Our next speaker is Roland Hall from University of Waterloo in Canada, and change of topic to water quality. Over to you.
Right. Well, thanks, John. Thanks for the opportunity to speak. Yeah, my talk is going to follow quite closely on the theme of that Chanel just provided to us, but take you to the aquatic systems and hopefully show you that there is an important role for paleo records in the management of quality and quantity. Of course, as I think Peck told us, increasingly, the world is less climate warming skeptic, and now the reality is upon us. And of course, there's a real opportunity for our fields, but a real responsibility for us to use the information that we can obtain to improve the way that we make decisions and adapt and modify for societal benefit. Now, many processes that affect the quantity and quality of our surface waters, they operate over a real broad range of temporal and spatial scales. I mean, from days, short-lived events of days and weeks, through seasons, years, decades, centuries, and millennia, and over a variety of spatial scales, from point sources that affect one part of a water body to in the entire water body, to the water body with its catchment, and even to sort of regional and subcontinental scales. These processes can act over that. And hopefully what I'll show you is that the information provided in sediment records is often one of the few, or maybe sometimes the only source of information that can span those kinds of temporal and spatial perspectives to understand the real drivers of change and the threats to degradation and limitations of our resources. Now, one of the things is that management and policy usually get initiated after the fact. That is, after some human desired use of the system becomes impaired or perceived to be threatened. And so we rarely have adequate sort of instrumental records of the pre-impact state. And yet resource management really requires answers to a number of very important questions here. What was that pre-disturbance state? And what is the range of natural variability? Those are extremely important in terms of managing what we can get a system back to. Can we identify, have conditions changed, and if so, how much, how fast, when did it start, and what were the processes that caused that degradation? Many processes operate at the same time. Climate variations, human pressure variations, they often overlap, and we need to be able to tease out the relative importance of these multiple stressors. If we can answer a bunch of these questions, we can assess how much improvement can be expected and where the effort should lie to bring about those improvements. Now, answers to each of these questions requires a long-term perspective, and so simply obtaining sediment cores from lakes and reservoirs and wetlands can tell us a lot about the changes that have occurred. And so, I mean, really, I'm sure most people know what paleolimnology here is, but essentially it's what most of us do using whatever evidence we can find, physical, chemical, and biological information in archives, in this case lake sediments, or to understand the changes in those aquatic systems. So the focus is on the aquatic systems. Oh. How do I get out of that? Hit the wrong button. Okay, so the lake sediment record provides this is really dying on me, this button here. Maybe I can use the mouse. The sediments provide a very rich source of information about the changes that have gone on inside of the lake basin itself, so the biogeochemical and biological changes that have gone on as a result of a number of processes. But of course, we can also get some handle on changes that have gone on in the atmosphere and the climate, because that impinges directly and indirectly on the lakes, and changes that have gone on in the catchment, vegetation shifts, erosional changes, and so on. And as we've seen, I think Chanel showed, and Rob as well, a lot of the changes have taken place in the 20th century. And so a lot of the emphasis is on getting understanding these recent changes, the past few centuries or the past millennium or two. And we can often obtain these kinds of records with fairly simple devices that obtain fairly undisturbed records. And we routinely slice these now at fairly close intervals, so even at sort of quarter centimeter intervals, and we get close to annual, certainly sub-decadal resolution from most systems. All right, so if you read my abstract, I'll have to admit that I lied a bit. I promised that I would show you that these sorts of approaches are being used in very applied senses to help us manage and anticipate future change, and that I would provide examples from all over the world. I realized when I really confronted several months after writing that abstract with the reality of 20 minutes, I scaled back. So I got 2 examples, and they both happen to come from Canada, but I think they're really excellent examples that show how integrating paleo with modern studies and experimental approaches have allowed us to really identify controls on water quality and water quantity, and how they have really causing some paradigm shifts and providing some accurate information that breaks down misunderstandings. So I'm going to start with the first case study. I'm going to take you to the northern Great Plains region, so the breadbasket of North America here, and look at identifying controls of water quality in a system in the northern part of that in the province of Saskatchewan. Now, and this is an issue of lake eutrophication, so the enrichment of surface waters with the influx of nutrients. And this eutrophication is a severe problem around the globe. We've been studying it for decades, and we know a lot about it, but most of our information comes from temperate regions of North America and Europe, and fairly deep lakes that stratify thermally and that are limited by the supply of phosphorus. This region is quite a flat landscape. There's a thin veneer of water in the low parts of this landscape, and so that you have fairly shallow lakes, you have much less forest cover, a lot more wind, so they tend to be polymictic. The water column circulates. This puts it in communication with the sediments, the rich nutrient sources in the sediments, and they tend to be quite productive. And because they're productive, they can be climate sensitive. Changes in the duration of ice cover or even stagnant periods of a few weeks in the summer can lead to rapid anoxia of deep waters and fish kills and those sorts of things. And unlike many other regions of the world where we've been studying eutrophication, these catchments supply high amounts of phosphorus to the systems, and it tends to promote nitrogen limitation of the algal growth. And in those cases, you get these cyanobacteria that can produce toxins and foul the waters and impair the use of the waters, even to the point where they are harmful when used as irrigation water on crops, and the toxins kill cattle and those sorts of things, even in this system. Okay, so I'm going to take you to the Qu'Appelle Valley of Saskatchewan. It covers about 52,000 square kilometers. I think that's about the size of Switzerland for those in the Pages office. It spans about 400 kilometers from one end to the other. There's a series of 3 headwater lakes here, a chain of 4 downstream, and then another 2. So it's a flowing system from west to east here. This landscape is heavily used for agriculture. It's also heavily used for recreation and fisheries and so on. I'll point out here the city of Regina, about 300,000 people, significant point source of nutrients that impinge here first on this Pasqua Lake, and I'll talk about that one a little bit. Water quality follows a gradient here from oligotrophic or mesotrophic, fairly nutrient poor, less nutrients in these westward ones, and increases to hypereutrophic with all sorts of water quality problems and noxious blooms as you go further downstream. Now, there's been really inadequate historical records, so understanding what controls water quality in this system is limited, but there's at least 3 main factors that might control it. This is an arid part of the world, so slight changes in the precipitation evaporation balance can cause lakes to draw down and nutrients and to concentrate, salinity to increase, and so forth. So climate can really be a player here. There's nothing like an average climate in Saskatchewan. It's either drought or it's very wet. This is one of the most heavily modified landscapes on Earth. 95% of the land area has been converted to intensive agriculture, mostly crops, but increasingly livestock. And then human demography changes as people have moved from the countryside to the cities. About half of the population has become increasingly concentrated into the cities. All right, and many of those changes have acted at over the same time scales. And in particular, the absence of pre-agricultural records has made it very difficult to manage effectively water quality in this setting, as I'll show. So we tried to get longer time series of data, went out, I joined Peter Levitt. This is really the leader, Peter Levitt. I joined the project as a postdoc, and some of the stuff that I'll show is stuff that he and his lab have taken on well after I've left. But we collected sediment cores from each of those lakes. This is from Pasqua Lake, the first one to get the nutrients. We measured a whole bunch of different things, but I'm going to show you a pigment record, fossil algal pigments. We can track changes in the composition and abundance of algae. And this is the graph from Pasqua Lake. This is the first lake to receive the sewage from the city of Regina. So here we have a 200-year record back to the 1800s. I've marked the onset of European settlement and agriculture and the onset of tertiary sewage treatment. And I'm going to make three points from this graph. One is that there was an abundance of pigments from filamentous blue-green algae and nitrogen-fixing blue-green algae, which suggests that water quality was naturally poor, it was quite productive and suffered from nitrogen limitation, and that the early agriculture didn't really stimulate production as people had thought it would be responsible for some eutrophication. Secondly, despite this high baseline productivity, conditions got worse, notably in the 30s to 60s when population started to grow in the cities. And the third point here is that even after onset of tertiary sewage treatment that removed phosphorus, because that's what the thinking was, that phosphorus controls eutrophication, algal biomass has continued to increase, and in fact the variability or predictability has become higher. To put this in a landscape perspective, what I'm trying to show here, this lake number 2 here is Pasqua Lake, the first one to get sewage. There's 2 upstream lakes. And what I'm plotting here is the percent increase in total algal biomass estimated from beta-carotene, a pigment found in all algae, above the pre-1850 level, pre-agricultural levels. So what you see is Pasqua Lake here dominates the signal. You also see increases in algal biomass for a couple of lakes downstream, but the ones upstream of the urban inputs and the ones at the very far end have not seen changes or increases in algal biomass. So it seems to be a pattern consistent with strong impacts of a point source rather than a regional driver like climate or agriculture. And I want you to note that some of these big increases, about 300% increase in biomass, has occurred after 1977 when tertiary sewage treatment caused phosphorus loads to the system to decline by 85%. But nitrogen loading has remained at all-time highs. So all of these points suggest that urban point sources of pollution rather than climate and agriculture are the dominant drivers of eutrophication problems, and that it's probably nitrogen rather than phosphorus, and all of the effort has gone into managing phosphorus in this system. Now to further look at this, we've used stable isotopes. This is something that Peter's taken on beyond any role I played in this project to look at nitrogen stable isotopes to get a better handle on the sources and the role of nitrogen in this system. And this is a really interesting graph, 150 years plotted here, and the sedimentary Delta 15N signature here. The upstream reference lake shows very little change in the nitrogen stable isotope composition, whereas the first lake to receive the urban sewage shows this dramatic pattern of increase after the 30s and particularly after the 50s to values that are almost equivalent to the N15 signature of the sewage effluent. Okay, so I think his mass balance modeling suggests that 85% of the nitrogen to this system is coming from urban sewage. We also see that this sedimentary isotope signature for nitrogen is linearly correlated to the loading of sewage, suggesting a very strong role of sewage on the nitrogen in the sediments. And there's a strong correlation between the isotopic changes over the last century and increases in the abundance of green algae and the cyanobacterial algae that cause the water quality problems, indicating that these bloom-forming algae have increased because of the urban nitrogen loads. And again, just to show, this is the last 20 years signatures of Del 15N along the lakes in that chain from west to east. And again, you see that really the first 3 to 4 lakes have a strong imprint of the sewage-derived nitrogen, whereas upstream and downstream lakes are much less affected. When you put all of this together, there's some real clear messages for management, and none of these things were known, would have been known or knowable from records other than what came out of the sediment records. So these lakes were naturally productive. This was not a general thought when I started into this project in the around 95. But despite naturally poor water quality, it is possible to achieve good reductions and control some of those issues, but we can reduce total algal biomass by 300%. And in fact, the nuisance-causing algae can go down by about 500%. But if we're going to improve water quality, we have to control N, nitrogen, and have to remove that from sewage. And that's a costly thing for a city of 200,000 people or 300,000 people to do. So that is an impediment. Improvements, even if you invest the millions of dollars that are needed, the improvements are only going to occur in the first 3 lakes. Maybe the 4th lake will see some improvements as well. And when you incorporate some mass balance modeling estimates, you can provide this sort of information that complete lake recovery is going to take a bit of time, and so the public is going to have to be patient to invest this money and then wait for a few decades to see recovery, because there is a lot of internal loading that's going on in this system. All right, so there's one example about water quality. I want to take you to the Mackenzie River Basin and show you how we've been using information in sediment archives and also tree rings to get a sense on what's controlling water quantity changes through a system. Now again, Canada is known for great water quality and an abundance of water, but I'm going to show you that we have poor water quality, as I've just shown you, and there are some threats to the supply of water to meet our needs. So taking you to the Mackenzie River Basin here, covers 20% of Canada's land mass. It's almost the size of Europe. It is a water-rich basin. It provides 60% of the freshwater flow that leaves Canada's landmass and goes into the Arctic Ocean. And I'm going to take you to the very southern part of that catchment, to the headwater region, and the study took place here in the Peace-Athabasca Delta, the confluence of the Athabasca River that drains from the Columbia Icefield, and the Peace River. Both of these rivers go about 1,000 kilometers along until they come to this delta. It's a UNESCO World Heritage Site and a Ramsar wetland of international significance for its biological productivity and cultural heritage and so forth. It's protected in Canada's largest national park. It's a very flat landscape. The rivers are northward flowing, so the Athabasca comes up and makes an active delta here into Lake Athabasca and continues to flow and meet the Peace River that comes mostly northward. I'm at 2 minutes? Okay, better move along here. A particular concern is, or an important process here is ice jam floods that periodically cause the rivers to rise in the north and backflood and flood huge areas here. It's a fairly arid region, so it's one of the few ways to fill up perched basins. Now, ever since 40 years ago, a dam went in on the Peace River, and ever since then, and it corresponded with a time when flood frequency was perceived to have declined and water levels to have gone down and caused ecological damage. So for 40 years, it's been widely believed that this dam caused issues. It led to lawsuits and to us doing a study here. And we were able to show that, in fact, the post-dam period was not outside the range of natural variability, and that the drying trend and the reductions in flooding happened decades before the onset of the dam, and that it was strongly controlled by climate. And there's increasing concerns these days about the effects of climate change. There's dwindling headwater glaciers and snowpacks. At the same time, when industrial consumption is increasing here's where the Athabasca oil sands sit. And we have, we base our decisions on 40 years of hydrometric data that show, small changes, but you certainly can't appreciate the role of climate in driving water quality resources. So what we've done is we've used a tree ring record to get at climate change and multi-proxy analyses of a bunch of sites throughout this delta to understand changes in hydroecological conditions here, and I'll try and get through this quickly. We have an oxbow lake where we have banded sediments. Dark bands are flood intervals, light bands are the non-flood, and we have a magnetic susceptibility record that tracks those changes. We have a upland basin that's the least flood prone. It takes sheet flow 5 kilometers to get into here. So you've got a mature forest. It's responding more to the climate than it is to the river influence. 2 lowland lakes, one up along a river channel and one near a former embayment of Lake Athabasca here that respond to changes in the water levels of Lake Athabasca and the open drainage flow network. And we've got a lagoonal pond here out on an island that is an independent marker of lake level changes in Lake Athabasca. As water can flow through the sandbar and raise the level of the lake, and when it does, you have autochthonous production dominating at a low C to N ratio, and as the lake level goes down, the lake shrinks, terrestrial vegetation encroaches, and the C to N ratio rises. So it's going to take me a couple more minutes to get through this presentation. We have a 1,000-year record here. Here's a tree ring based, using stable isotopes, tracking the warm and moist medieval period, transitioning into the cold, arid Little Ice Age, and then warming after the Little Ice Age. And we've got these gray bars here showing glacier advances. Here's a flood record from that Oxbow Lake. Here's water balance estimates from the cellulose 018 records, diatom records from these. This is the climate-sensitive perched basin, the lowland basins, and then our inferred proxy of Lake Athabasca levels. What I want to show you is there's tremendous change, and the change coincides with the main climate periods there, and they play out in very complex ways at the landscape scale. So for example, we have evidence of very strong river inputs here on these 2 lakes, coinciding with evidence of frequent and massive ice jam flooding, so depleting the water balance through the medieval warm period. But we don't see any evidence in this one lowland lake, probably because Lake Athabasca levels were low. As we transition into the Little Ice Age, we get a sharp shift to reductions in flood frequency and magnitude. We get strong indication of an arid climate causing the lake to nearly dry out. And this lake showed a similar pattern initially and then deviated with strong indications of being inundated under a big water body, also this pad 9, in sequence with Lake Athabasca levels going up. And then we have this sort of signal of further reductions in flooding, greater evaporation, and these lakes becoming closed drainage and Lake Athabasca water levels going down. So tremendous amounts of change, really important stuff for management. And we've got this 40-year record of instrumental records that managers are trying to understand. And it's led to really incorrect conclusions that the dam has been the cause of this rather than the climate changes that have gone on. And so we've been able to reconcile and sort of put all of this complex behavior in the landscape into sort of what I call hydrographs, sort of patterns of hydrographs, stream discharge, seasonal changes in the quantity and timing of discharge on the main rivers. So our evidence would suggest that during the medieval period we had a very early and high peak discharge, a very flashy spring freshet that produced ice jams as the rivers were still covered with ice. But then in the absence of thick snowpacks and glaciers in the high elevations, that you had low flows during the summer months. And that promoted low levels on Lake Athabasca. We went into the Little Ice Age, we had much more protracted snowmelt, and so the water coming down the river came too late to form ice jam floods. So we see a reduction in floods, but melted throughout the summer and supported much higher flows through the summers, which led to an elevation of Lake Athabasca. So Lake Athabasca would have flooded most of the green areas and blue and aqua here on a fairly constant basis. So a 2.3 meter rise in the lake because of those hydroclimatic changes. And then we've been shifting back to a warmer, moister climate, but we don't have the snowpacks or the glaciers to neither produce the spring freshet that produces the ice jam floods, and the summer discharge has been going down, causing shrinkage in lake levels. And so here again, we've gone from high peak spring peaks to delayed onset of spring peak, but much higher flows through the summer in the Little Ice Age. And now we're on this trajectory towards a situation where we're not getting the ecologically important floods for this landscape, but we're also not getting the continued high levels of flow that is required for, that we need for industrial developments and so on. And so this, again, provides some real, I'm nearly done now, some real messages for lake management. First is that this delta is much more dynamic and sensitive to climate change than we ever anticipated. Who would have thought that the headwaters of the Rocky Mountain would be driving this system, this flat ecosystem 1,000 kilometers downstream? And so and management is continuing to try and manage it as a static system in the face of all this variability. The other thing is that the drivers of change operate at very broad spatial and temporal scales, and our instrumental records have been really inadequate and led to erroneous conclusions about what's causing the recent changes. And we have some real warnings that the supply of water is becoming inadequate to meet the needs of the ecosystems as well as the development along the way. And this is happening at the same time when indigenous communities north of this system are gaining ownership and allowed to make decisions about these resources. And the conflicts that are at risk here are very high. And the Athabasca River is maybe the watershed of highest importance in Canada to manage effectively because of the oil sands and the consumption of water that's going to happen there. So I hope I've shown you that there's a real role for paleo to play in informing management and helping us adapt to the future. These sorts of studies are going on all around the world and starting to make some real inroads into policy and practice. And I thank you for your attention. And